Hello, welcome to Chemistry Chapter 5B, Lecture 1. The first on your own problem that we are going to be working for this lecture is on page 144. And up at the top, so let me first start out and tell you what you need. You need your notes, 5B in Chapter 6. You need a periodic table. You need your book. And you'll need a calculator. So before I get started, if this video helps you, please consider buying me a coffee. There's a link in the description box, or you can scan this QR code. Okay. So this is typically the first lecture after fall break, if this is when you're watching it. So to go through a few terms in your notes before we get started with our calculations, up at the top of your notes, okay, maybe in this space here, I want you to write this equation, or really it's a methodology since there's not an equal sign. So atoms or molecules, and then put a double arrow, and then moles. We'll talk about what moles are in a second, and then another double arrow, and then grams. Okay, so you will need to have this memorized. I usually tell students on the day of the test, write that up at the top of the test before you do anything. So, going through the vocabulary here in second half of chapter 5, the atomic number is the number in the periodic table above the element symbol. So, for example, helium, it's 2. Aluminum, it's 13. Sulfur, it's 16. That corresponds to the number of protons in the atom. So we're not really going to be using that number right now, but we will get to that. The atomic mass, okay, that is the number beneath the element symbol. So on this periodic table, carbon, 12.01, oxygen, 16.00. That tells you how many grams are in a mole of that element. Okay, so the bigger the atomic mass, the heavier the atom. Okay, we're going to talk about this in a minute, but you do need to memorize what a mole is. It's Avogadro's number, and it's 6.02 times 10 to the 23rd of anything. Okay, but what we're going to be talking about is chemistry, and I'll talk about through this in just a second. Okay, so usually the term mole is used in chemistry or physics or science. The atomic mass number, all right, tells you, so atomic mass number is the same as this atomic mass number, that number below, like for oxygen it was 16.00. It's how many grams are contained in 1 mole. It also means how many AMUs, atomic mass units, are in 1 atom. I'm not going to be using atomic mass units. I know that the book does. I prefer a different methodology. So what that means, so you need to know what that is as you read the chapter, but I won't be using it. So how many grams are contained in 1 mole? That means with oxygen, for example. Well, let's go with carbon since I haven't marked that up. For carbon, there's 12.01 grams in every 6.02 times 10 to the 23rd atoms of carbon. Okay. So why are we using this crazy big number, and what the heck are we talking about? So 1 mole is equal to 6.02 times 10 to the 23rd. Now, it's of anything, but we typically only use it for atoms or molecules. So a mole is just a counter. Okay, it's a way of counting things up. So, for example, how much is a dozen? All right, a dozen is 12. So A lot of times we count in dozens. Say a dozen eggs. Go buy me 4 dozen eggs. You know it's going to be, that's 48, but it's a little bit easier than saying go buy me 48 eggs. Go buy me 4 dozen eggs. Okay? When we talk about years, sometimes in history you'll talk about decades. Well, a decade is 10 years, right? So you can say 3 decades, you know, you mean 30 years. It's a counter of years. Okay? A mole is just like how 12 is a counter and 10 is a counter with decades. A mole is just a counter, a counting device for atoms. Because atoms are so small, we need a big number. Now, where did they come up with this crazy number? Well, Avogadro determined, or I'm not sure about that. We do call it Avogadro's number. So you can Google Avogadro if you want, but that there are 6.02 times 10 to the 23rd atoms in 12 grams of the most common isotope of carbon. Okay, so carbon was used kind of as a yardstick here. That's another thing. A yard is 3 feet, right? So that's used as a counter in football. So there's 6.02 times 10 to the 23rd atoms in 12 grams of the most common isotope of carbon. So we use that as our counter, all right? 1 mole, 2 moles, 3 moles. Now, it's different. How much a mole is different based on the element, because elements are lighter and heavier than each other. So when I'm in class, there's in 18 grams, so this is on page 147, in 18 grams of water, that's this right here. I don't know how well you can see it in this graduated cylinder. That's a mole of water. That means there's 6.02 times 10 to the 23rd molecules in 18 grams of water. There's also, for sodium chloride, there's right here in that beaker, there's 6.02 times 10 to the 23rd molecules of sodium chloride. It happens to add up to 58.5 grams. There's a watch glass with iron filings on it. Those iron filings, if you were to add up all of the atoms of iron, there would be 6.02 times 10 to the 23rd of them. Also, that corresponds to 55.8 grams. If you have a helium balloon, all right, inside this helium balloon here, there are 6.02 times 10 to the 23rd atoms of helium. Just so happens that's 4 grams of helium. All right, so on the periodic table, we can see that. So helium has a mass of 4. That means there are 4 grams per mole of helium. Okay, with sulfur, there's 32, almost 0.1, so we'll go with 32.1 grams in a mole of sulfur. So if you have 6.02 times 10 to the 23rd atoms of sulfur, it will weigh 32.07 grams. All right. So you'll get used to it if it seems confusing at first. So let's go ahead and work a problem. Let's open up to page 144. And on your own 5.5 says, what is the mass of a calcium atom in kilograms? Now I want you to start to the far left of your paper. So we're going to do this using the factor label method, just like chapter 1. So this is on your own 5.5 on page 144. We're going to start at the far left, and we're going to use this system right here. It tells us that we've got 1 calcium atom. So we're starting here. So we have 1 atom, and the symbol for calcium is Ca. We're going to put that over 1. Now, I'm trying to go to kilograms. First I have to go to grams, but I have to go through moles to get there. So we put what we want to go to on top, moles of calcium, and what we want to cancel out on bottom, and leave a little space here, atoms of calcium. Well, this is one thing to learn, that if you have moles and then some unit other than moles, in this case atoms, the 1 always goes by the moles. How many atoms are in a mole? Well, it's right here. It's 6.02 times 10 to the 23rd. Okay, we've made it here. We've made it from atoms to moles. Now we want to go to grams. So we have grams of calcium on top. We want to cancel out moles of calcium. If it's moles and some other unit, the 1 always goes by the mole. And you get the number of grams in a mole for calcium from the periodic table. Well, we're going to round to the nearest tenth. All right, that's what the periodic table in your book does. So 40.1. So that comes from the periodic table. Finally, we need to go to kilograms because the author made us do an extra step here. Usually we stop at grams. And we cancel out grams. So this is just like what we did in chapter 1. The 1 goes by the bigger one, kilograms, and there's 1,000 grams in a kilogram. Okay, so let's put this in our calculator. We're starting with 1 atom of calcium. 6.02 times 10 to the 23rd is on the bottom, so we divide, and remember how to put this in your calculator, 6.02, second function, double E to the 23rd. I always hit enter after every one. Okay, then we multiply, so you might see that number's in your book, that 1.66 times 10 to the minus 24, but the author doesn't explain where that comes from. Now I'm showing you where it comes from. All right, we're going to multiply by 40.1, because 40.1's on top, and then we want to go to kilograms, so we divide by 1,000. So that's 6.66 times 10 to the minus 26 kilograms. Remember, your final unit's the ones that's on top in your last set of parentheses. All right, 1 atom of calcium doesn't weigh very much, and you wouldn't think that it does, would you? All right. So our next vocab term is molecular mass. All that is, there's nothing fancy about that, the sum of all the masses in a molecule. So instead of a single atom of an element, you have a molecule. Okay, so let's look at on your own 5.6, and this is on page 145. Okay, so this one it says, what is the mass of an Na2SO4 molecule in grams? And again, I'm not going to use this relationship here because the author's not telling you where that number comes from. We're going to get that number on our own, and it makes a lot more sense using this equation. So first of all, we have to add up the grams per mole of Na2SO4. So there's an extra step in these problems with molecules. So for sodium, we have 2 molecules. And if you look at the periodic table, sodium, right here, number 11, weighs 23. Again, 23.0. So that's 46. In this molecule, there's 1 sulfur atom. So there's 1 times, and each sulfur, look at the periodic table, all right, and that's 32.1. We're rounding up. So if you want to look at the rounded values to the nearest tenth, just go to your periodic table that is in the front cover of your book. Those are the numbers I'm using. You don't have to. You could do it 32.07. And then for oxygen, there's 4 oxygens. Each oxygen, look at the periodic table, weighs 16 grams per mole. So that's 64. So if we add those 3 numbers together, all right, we're going to get 142.1 grams per mole. So that's just our initial step. Now we can go through this. So we have, start to the far left, 1 molecule of Na2SO4. Put that over 1. That's where we're starting. Now we want to go to moles. So put moles of Na2SO4. We want to cancel out molecules. I'm just going to do MOLEC, Na2SO4. The 1 always goes by the mole if it's with another unit. Now, if it's mole over mole, that's different. We'll get to that in a little bit. How many molecules are in a mole? 6.02 times 10 to the 23rd. All right, and now we're going to grams. So grams of Na2SO4. We're canceling out moles. See, just go up 1 level and to the left, and that's what you're canceling out, moles. And you abbreviate moles, MOL. It's not much of an abbreviation, but that's the best we can do. Where does the 1 go? Goes by the mole. How many grams are in a mole? We just added it up, and it turned out that it's right above where I need, 142.1. All right, let's put this in our calculator. All right, we've got 1 divided by 6.02 times 10 to the 23rd. We know that's going to be 1.66 times 10 to the minus 24th. And then times 142.1. We multiply because it's on top. That's 2.36 times 10 to the minus 22. And the unit is grams. All right, beautiful. Okay, so those are the longish problems. We're going to do a few that are shorter now. If you'll turn over to 5.7 on page 151. That one says, how many moles of sulfur atoms are in a 50-gram sample of sulfur? Okay, so this time we're starting here with grams, and we're just going over to moles. So we just have 2 sets of parentheses. So we've got 50 grams of sulfur. So start with what the problem gives you. 50 grams of sulfur, put it over 1. We want to get moles of sulfur. We want to cancel out grams of sulfur. Where does the 1 go? Goes by the mole. How many grams of sulfur are in a mole? Where do you figure that out? You figure it out from the periodic table. Look here, there's 32.1 grams in a mole. So 32.1. So this is a pretty simple one. It's just 50 divided by 32.1. 1.56 moles of sulfur. That's how, if you have a 50-gram sample of sulfur, it's 1.56 moles. Okay, let's look at 5.8. That's right underneath. So that one says, how many moles of glucose, so C6H12O6, are in a 1.25 kilogram sample? All right. Well, because the author gave it in kilograms, this is going to be 3 sets of parentheses. But first we have to add up C6H12O6. So for carbon, there are 6 atoms. Each carbon atom weighs 12 grams. All right, that's coming from the periodic table. All right, if we're rounding to the nearest tenth, that'd be 12. So 6 times 12, 72. Hydrogen, there's 12 hydrogens. Each hydrogen weighs 1 gram per mole. So that's going to be 12, right? Hydrogen is 1. You don't have to do 1.01. And then oxygen, there's 6 of those. Each oxygen is 16 from the periodic table. So that would be 96. So that's 180 grams per mole. So that's how many grams are in a mole of glucose. If you have 6.02 times 10 to the 23rd molecules of glucose, it will weigh 180 grams. Okay, so now we're going to convert 1.25 kilograms of C6H12O6. Getting a little messy here because I'm at the bottom. I need to go to grams. I need to cancel out kilograms. Okay, the 1 goes by the bigger one, 1, and we've got 1,000 grams in a kilogram. All right, so now we're going we want to know how many moles we have. So moles goes on top. We want to cancel out grams. Remember, grams is up on top over here. The 1 goes by the mole. Remember, it's moles in some other unit. The 1 goes by. And then we added it up. There's 180 grams in a mole. All right, so we've got 1.25 times 1,000. And then divide that by 180. And you've got 6.94 moles. All right, so you're going to get a whole worksheet. After the homework from the book, you're going to get a whole worksheet to practice on these. So practice makes much better. I won't say it makes perfect, but it makes you much better. So we'll give you plenty of practice. Okay, so in your notes, we've just got 2 more problems to work. 5.9 is the next one that we're going to work. So in your book, flip over to page 152. So that one asks, what is the mass of an NO3 sample if it contains 0.3 moles? 0.23 moles. All right, so we're just going from moles to grams. What is the mass? Moles to grams. You know, not using atoms or molecules here. But I am going to have to add up NO3 because that's a molecule, right? So for nitrogen, there's 1 of them. Each nitrogen, if you look at the periodic table, is 14. All right, so nitrogen there, 14. So that's going to be 14. And then we have 3 oxygens. Each oxygen is 16. You probably have that memorized. You're going to use these so much that a lot of them you'll get memorized. So that would be 48. So that is 62 grams per mole. So 1 mole of the NO3 molecules weighs 62 grams. Okay, so let's start with what we've been given in the problem, 0.23 moles of NO3. Put that over 1. Going from moles to grams. So put grams on top. That's where we want to end up. We want to cancel out mole, so let's put that on bottom. The 1 always goes by the mole, and then we just added it up. There's 62 grams per mole. So pretty easy here. We're just going to do 0.23 times 62, 14.26 grams of NO3. If you have a 0.23 mole sample, this is how much it's going to weigh. Okay, our last problem is a fancy word that you're going to do a lot in Chapter 6, but this is going to be your first foray into that. Using moles in a chemical equation. The coefficients correspond to the number of moles in the substance that participate in a chemical reaction. All right, let me show you what that means by working problem 5.10. Okay, so we are at the bottom of 155. So that problem says a chemist obtains a 122.3 mole sample of ammonia. If the chemist allows this sample to decompose, how many moles of hydrogen gas will be produced? Okay, first, we have to get a chemical equation. So this is a decomposition reaction. We have NH3. That's going to decompose into N2 plus H2. Okay, both of these are homonuclear diatomics. All right. Now we have to balance. All right, we must be balanced. So we need a 2 to balance nitrogen. We have 2 nitrogens here, so now we have 2. And now 2 times 3, we need a 3 right here. Now I've got 6 hydrogens on each side. So now we're balanced. We're going to use those coefficients in this process. So it says we have a 122.3 mole sample of NH3. I'm going to put that over 1. I want to know how many moles of hydrogen. So we put moles of hydrogen on top. We're going to cancel out moles of NH3. Now what these coefficients tell you is the number of moles in this chemical reaction. Okay, so it tells you that there are 3 moles of hydrogen, so it just comes from that stoichiometric coefficient. 3 moles of hydrogen per 2 moles of NH3. So this is a case where you don't have a 1 go by the mole unless the coefficient is 1. So it's just the coefficients in front. So our calculation here is 122.3 times 3, so times 3 on top, divided by 2. So that's 183.45 moles of hydrogen. So what that means, what does that mean? It means if you start out with 122.3 moles of NH3 and you do this chemical reaction, after it's over, you will end up with 183.45 moles of H2. This parenthesis, that ratio of coefficients, it's the ratio of moles, that is called stoichiometry. And that is the topic for almost the entirety of Chapter 6. And you will work stoichiometry problems in almost all the chapters. Not in 8 or 9, but all the rest of the chapters you will work stoichiometry problems all the way through Chapter 13. All right, so very important concept. You just barely initiated you to it. So your next lecture in Chapter 6, you really get into it. So the homework... you will do review questions, page 161, 7 through 10, and practice problems, page 162. You can do 4 through 10. All right, that does it for this lecture. Just want to remind you real quick that if this lecture helped you, consider buying me a coffee. It's a $3 donation, and there's a link in the description box, or if you prefer, you can use the QR code. Also, I'm going to include a link to the vinyl of the day, and the album is from a rock band called Kansas. They are from Kansas. This album is from 1977. It's called Point of No Return. Very, very cool album cover. And one of my favorite bands of all time, a band that I have seen 16 times in concert. So, yeah, give this a listen, maybe if you like to listen to music while you work homework. So, that does it, and I will talk to you next time.